Hi, I'm Karthikeyan and I would be presenting our research work LRPlan, which is a multi-agent architecture for the planning task. This work was done with my collaborators at IIT Delhi and Microsoft. Real world in general has many complex planning problems, which comprises of both explicit as well as implicit constraints. Explicit constraints are stated directly by the user in the input query, whereas implicit constraints are unstated because of them being common sense in nature. So let's understand this with the help of a travel planning query. For example, could you create a travel plan for me from Delhi to China spanning 5 days? The trip should cover Shanghai and Hangzhou with an allocated budget of $500. So far, the constraints being introduced are explicit in nature. But for a plan to be valid and acceptable in real world, it also need to satisfy some common sense constraint. For example, the minimum number of nights criteria need to be obeyed for a particular accommodation. The attraction choices should not be repeated and many other common sense constraints. So to study this problem, we consider two data sets. The first one being TravelPlanner, which comprises of several travel planning queries, and we expect the system to return a day-wise travel plan, which would be evaluated later in terms of the percentage of implicit and explicit constraints being satisfied. We also study time arena dataset. A time arena dataset involves solving multiple tasks subject to subtask dependencies and to minimize the idle time. So we reformulate the existing time arena dataset to a static setting, and we also introduce new evaluation metrics for it. So it spans across like three different domains: cooking, laboratory, and household tasks. And it would be finally evaluated based on the number of tasks being successfully completed, also reducing the count of violations. So the challenge over here is off-the-shelf LLMs and LRMs struggle adhering to both explicit and implicit constraints. As seen in the trial planner dataset, the state-of-the-art LLMs and LRMs, large reasoning models, they perform poorly on the trial planner dataset, having a final pass rate ranging between 4 to 11%, which is quite low. But what's interesting to notice over here is LLMs do a better job on the implicit constraints and LRMs do a better job on the explicit constraints. So we ask this question, how can we combine the benefits of both LLM and LRM? So our contributions, so we contribute a multi-agent architecture which synergistically combines the benefit of LLMs and LRMs for the planning task. We also reformulate the existing time arena dataset to a static planning setting and also introduce new evaluation metrics. We do a comprehensive evaluation on two domains and two model families, GPT and DeepSeek. And we observe substantial improvement in both accuracy as well as cost efficiency. So our solution LRPlan is a domain independent architecture comprising of like two phases, the training phase and the test phase. In the training phase, we have several training samples and we extract several insights from those samples, patterns, rules, and correction insights. These insights would be appended along with the input query in the test phase to generate the final output plan. Now let's look at the training phase in detail. For example, in the travel planner domain, we could have some training sample like this, which would be passed on through any reasoning model like DeepSeek R1, which would eventually generate a reasoning trace followed by an output. This output would be validated to either correct or incorrect. The validator could be a human, it could be a LLM, or it could be any deterministic way of validating the output. So we repeat the same thing for several training samples. Once we have this corpus, we pass it through several meta agents in the training phase. The first one being pattern recognizer, whose job is to identify the patterns followed by the system in generating a successful plan. Pattern recognizer would analyze the reasoning traces and find interesting patterns which would help to generate a correct plan. These patterns would be passed on through a rule extractor, which would extract actionable rules. Parallelly, the training query and the reasoning traces would also be passed on to a self-corrector, which would extract self-correction insights. So we will see in the later stage in the test phase how these insights are being used to generate the plan. So let's move on to the test phase. In the test phase, once we have the patterns, rules, and correction insights, on the arrival of a new test query, we append it with the patterns and rules and pass it through a planner to get the first initial plan. This initial plan would be passed on along with the correction insights to the refiner to generate the final plan. The thing to notice over here is the planner is a LLM and the refiner would be a LRM. So the LRPlan architecture, we have initial training queries, we pass it through a reasoning model to get the reasoning traces and the output, which would then be passed on to through several meta agents in the training phase to get the patterns, rules, and correction insights. These insights would be used along with the input query in the test phase to get the final plan. So in the travel planner, we observe that our architecture LRPlan performs better than the direct strategy, which is standard prompting, chain of thought, and also several other multi-agent architectures like the AutoGen AutoBuild, multi-agent debate, and the expel. We observe similar performance in the DeepSeek family as well. So the LLM which is used for the GPT family is GPT-4o, LRM being O3 mini. And for the DeepSeek family, we use DeepSeek V3 as the LLM and DeepSeek R1 as the LRM. We observe similar results for the TimeArena-Static dataset on both GPT and the DeepSeek family. So when we were analyzing the cost incurred in our architecture, we observed that the LR plan uses very less number of tokens for completion. Also, it makes just 2 API calls compared to other multi-agent architectures. As part of the ablation, we study the impact of each meta agents in our architecture. In both TravelPlanner and TimeArena-Static, we observe that the LR plan with all meta agents in action produces the optimal result. And we also try several LLM-LRM combinations in the test phase. In the test phase, we have 2 agents, the planner agent and the refiner agent. So we try out all 4 possibilities of LLM-LRM, and we observe that across both the datasets, the planner being the LLM and the refiner being the LRM produces the optimal result. So the key experimental observations over here is LLM planner plus LRM refiner would outperform all other possible LLM-LRM combinations in the test phase. As we have seen in the initial ablation, all meta agents in the training phase do contribute. LRPlan achieves superior accuracy with just 2 API calls at the inference, one being used by the planner and then another one being used by the refiner, compared to 5 to 6 API calls in other multi-agent architectures. So what makes our LRPlan unique? It is a multi-agent architecture which learns from experience. It does not require any domain-specific human effort, and to the best of our knowledge, we are the first one to study the LLM-LRM synergy in the multi-agent architectures. This work could be extended in several directions. One direct way is to adapt it from the static planning to the online planning. And we could also augment the LRPlan architecture with formal tools and formal solvers to further enhance the performance. And we also plan to study this LRPlan architecture on diverse domains. The code and data which was being used in our work can be found in our GitHub repository. Thank you.